Orbital resonance is one of the most fascinating dynamics in celestial mechanics, a subtle yet powerful rhythm that shapes the architecture of our solar system and beyond. At its heart, resonance occurs when two or more orbiting bodies establish a simple numerical ratio between their orbital periods. For example, if one moon circles a planet twice in the same time it takes another to complete one orbit, they are said to be in a 2.1 resonance. These ratios, 2:1, 3:2, 4:3, and so forth, form a kind of cosmic harmony, and like the notes in a musical chord, they can either create stability or introduce tension. This delicate balance is governed by gravity. Each orbiting body tugs ever so slightly on the others, and when their cycles line up in repeating patterns, those gravitational nudges accumulate. Sometimes the result is a stabilizing influence, locking objects into predictable motions that can persist for billions of years. Other times, resonance amplifies gravitational interactions to the point of chaos, ejecting bodies from certain zones or carving out empty spaces in the cosmic landscape. In both cases, the effect is profound. It is resonance that sculpts planetary systems into their enduring forms. One of the most famous examples lies with Jupiter's three large Galilean moons, Io, Europa, and Ganymede. These moons are locked in a 1-2-4 resonance. For every orbit Ganymede completes, Europa makes 2, and Io makes 4. This configuration is not mere coincidence. It keeps their orbit stable, while also driving fascinating geological activity. The constant gravitational pulling and stretching, especially on Io, generates tidal heating that fuels its violent volcanic eruptions, the most intense in the solar system. Europa, under similar stresses, likely harbors a subsurface ocean beneath its icy crust, while Ganymede, the largest moon in the solar system, is pulled into a steady rhythm that helps maintain order among the trio. Resonances are also at work in the asteroid belt between Mars and Jupiter. There are certain orbital paths, called Kirkwood gaps, are mysteriously empty of asteroids. These gaps exist because the asteroids that once occupied those regions fell into resonance with Jupiter's massive gravitational field. For example, if an asteroid orbited the Sun 3 times for every one of Jupiter's orbits, it would receive repeated gravitational kicks at the same points in its orbit. Over time, those kicks destabilized its path, ejecting it from the zone entirely and leaving behind a gap. In this way, resonance both clears and organizes space. Beyond our solar system, astronomers have identified exoplanetary systems where planets are similarly caught in resonant chains. These resonances not only reveal how planetary systems evolve, but also provide clues about where life might be possible. Stable resonant systems can nurture environments long enough for life to emerge, while chaotic ones may doom planets to instability. In the grand story of the universe, orbital resonance is like a hidden conductor, setting the rhythm of celestial bodies. It reveals how gravity weaves order and chaos together, shaping worlds, sculpting belts of asteroids, and creating the cosmic music to which the planets dance.